This
I am ready.
conference will now be recorded.
Yes, sir, you can start now.
Okay. So good afternoon, everyone. I welcome all of you most heartily to the webinar 2.0 on recent trend in high frequency application, conducted by Department of Electronics and Communication Engineering, Swami Vivekananda Institute of Science and Technology. This is an exclusive initiative of EC department on capturing the fundamental concept of high frequency application by experts from IIT BHU for PG and UG students during this pandemic caused by COVID-19. I warmly welcome our honorable speaker, Professor Somak Bhattacharyya from IIT BHU. We are indeed grateful to Professor Bhattacharya for graciously and readily accepting our invitation. Although he does not need an introduction, let me brief about his contribution. Dr. Somak Bhattacharya was born in Kolkata on 31st July 1982. He passed physics honors from Scottish Church College in 2003. He received both BTech and MTech from Institute of Radiophysics and Electronics, University of Calcutta in 2006 and 2008 respectively. He had carried out his MTech thesis in Giant Meter Wave Radio Telescope, that is GMRT, of Tata Institute of Fundamental Research, TIFR. He is the recipient of University Gold Medal due to securing first position in FinTech. He had also served as a lecturer in Academic of Technology in 2009. He received his PhD degree in 2015 from IIT Kanpur. He had continued as a senior project engineer in the Department of Electrical Engineering, IIT Kanpur, for a brief period of 6 months, after which he had joined Department of Electronics and Communication Engineering in IIT Allahabad in December 2015. Since 2016, he is working as assistant professor in the Department of Electronics Engineering, IIT BHU, Varanasi. He has published more than 30 international journals and 80 reputed peer-reviewed international and national conference proceedings. He is currently supervising 4 PhD students. He has received the prestigious Young Scientist Award from International Union of Radio Science, URSI, 3 times. Electromagnetic Theory Symposium 2013 in Hiroshima, Regional Radio Science Conference in 2015 in New Delhi, and Asia Pacific Radio Science Conference in 2016 in Seoul. Owing to his contribution in the area of radio science, UISI has conferred him honorary lifetime membership. He has served as a potential reviewer to nearly 40 journals, including IEEE Transaction on Antenna and Radio Propagation, IEEE Antenna and Wireless Propagation and Letters, Electromagnetic Electronics Letter, IEEE Microwave and Wireless Component, IEEE Photonics, Nature Science, Scientific Reports, and Springer Applied Physics, etc. He is the technical program committee member of a number of conferences like Indian Conference on Antenna and Propagation, INCAP 2018, Indian Microwave and Radio Wave Radio Conference, IMARC 2018 and 2019, IEEE INAE AI workshop on electromagnetics, IIWE 2018, IEEE Region 10 Conference, 10Con 2019. He has also served as a local organizing committee member of URSI Asia Pacific Radio Science Conference 2019 in New Delhi, where he has also served as one of the session conveners in Fields and Waves. He has recently organized 2020 UISI Regional Conference on Radio Wave Radio Science in IIT BHU Varanasi, where nearly 300 delegates were present all over India. Very recently, Professor Bhattacharya has received IEEE senior membership. His current research area includes metamaterial, metasurface, periodic structure, optomicrowave devices, etc. Now I would like to hand over the session to Professor Bhattacharya, and we are eagerly waiting for his lecture. I would look forward to wonderful events to follow.
Okay. Okay. Am I audible?
Yes, sir.
And am I visible now?
Yes, sir.
Okay. Okay. So thank you, Professor Sarkar, for the introduction. I don't know how much I really belong to, but what I am just going to tell you people, that is about the recent trends in high frequency applications. So what I will do first, that I will just let you know about some of the recent applications and recent trends in the high frequency domain applications. Now, what I will just suggest, especially this particular lecture I have prepared in keeping in mind for my junior colleagues, especially who have just started their career in electronics engineering, maybe in the second or third year. What I am assuming that you are having a very basic level of the background of analog communication, and accordingly, I had tried to prepare my slides. If I am going somewhere, means you know that somewhere, if my lecture is going somewhat above your head, please please don't hesitate to ask me any question, maybe at the end of your presentation or end of my presentation. So just let me ask from the organizer, so what will be the mode of the question answer session? Will it be at the last or in between? Can I take
last session?
Last,
after
okay.
your lecture. Yes.
Okay, okay. So now can I make myself can I make my video off?
Yes.
Okay, okay. Thank you. Am I audible? Fine. Is it okay?
Yes, sir.
Yes. Yes.
Okay, okay. So what I am doing, that I'm going, as I have told you, that I'm going to talk about the recent trends in high frequency applications. And I am Somak Bhattacharyya from IIT BHU Varanasi. So where we are from, that yes, we are situated also in India, not in West Bengal. I live in UP, very close to the border of Bihar. And Varanasi, if you can see from this figure, I think that this cursor is available. This cursor is visible, right? My cursor is visible?
Yes, sir, it is.
Okay, okay, thank you. So this one, you can see that as you have known, that the people who have not visited our place, Varanasi, it is situated on the right at the bank of the river Ganges, okay? And also what we are having, that this particular one, this is very much famous. The place is very much famous for its, you know, that the number of ghats. In fact, it's a scenic beauty that once you will have a very wonderful boat ride during the afternoon or evening time in the ghats of river Ganges, and each and every distinct ghats has its each and every distinct salient features. So once you will get the chance, I will just ask you to visit us. And this place is also very much awesome, and it's an awesome experience that if you can visit the famous Ganga Aarti, and there is a ghat which is known as the Shashwamed Ghat, which is the most famous ghat. And what you can do, one can come over here, and it means easily, or by taking from the boat itself, or even sitting at the ghats itself, one can view the famous Ganga Aarti over here. Now what we are, basically we are having the campus, the Indian Institute of Technology, BHU Varanasi. This is we are co-located with the campus of Banaras Hindu University, or in short BHU. This campus happens to be the largest campus in Asia. And what you can have, how long it is? Well, from my home or from my residence to BHU main gate, it is something around close to 5 kilometers, and we are having a dedicated auto route. Now you can think that how big is the campus. Now, if you can just arrive over here, so this is the main gate of the campus, and if you can read Devanagari script, you can see over here it is written over here Kashi Hindu Vishwavidyalaya or Banaras Hindu University. And what I was just telling you a few minutes ago, the dedicated auto route, you can see that some autos are waiting for here for the passengers. Okay, so this is the main gate. So you have to enter within the campus, and then after going to some, means after traveling to some distance, you have to arrive to the original campus of the IIT BHU. So where we are, again you can see that this is the campus. Yes, so this is the aerial view. And what we are having, how you can have the demarcation? Well, you can think of, we are having a temple. This is also a Vishwanath temple, which is present within the campus itself. And you can see the height of this particular building or height of this particular temple. It is the tallest among the, or the peak is the tallest one in the city of Varanasi. Okay. And this temple basically segregates, you can think of the campus of IIT BHU from the bigger campus of, or from the larger campus of BHU. So thing is, once you are coming from the entry gate, take the blessings of Lord Vishwanath and welcome to IIT BHU. So what I will just tell you that from the very beginning, so I will now coming to some kind of technical issues. So what we are having, that from the very earlier days of the civilizations, people used to communicate. If you see that these are the different scripts I am presenting over here, and although we are not writing anything, each of them are carrying some significant meanings. For example, if you go over here, if you just concentrate over this particular symbol, what you can think of, this basically thinks of different symbols over here from railing from different religions. Okay, and in the ancient age, you already know that people used to communicate by using some kind of hieroglyphic script. Okay, or maybe in the age of Stone Age, people used to communicate by some means. So those are the some kind of earlier days of communication. And later what we are having, that, well, this is the first telephone which was discovered by Sir Alexander Graham Bell. Okay, and what you can see that what is the distinct features over here. Well, on those days, people also used to communicate. So what is the meaning of communication? Communication is nothing but you are having certain transfer of information. Okay, so what you can have, that once you are having this transfer of information, so these are some kind of earlier days of communication. And as the time progresses, people have jumped to some modern days of communication. All of us used to have this kind of, you know, that some kind of wall hanging television nowadays to everyone's home. This is, and nowadays organic LED televisions have already come out in the market. Some of the laptops, I think that most of you will have, and also will have the some kind of, you know, some digital cameras, and also what you can have some kind of receiver systems. So all of them are omnipresent within the modern day communication. And what you can do, that all these things, or many of these things, have been embedded with most of you, those who are using this particular device, which is known as smartphone. And this particular smartphone, you already know that this will have a number of applications, right? Or you can not only we used to make some kind of phone call, we used to pass some kind of information, or we used to pass some kind of, you know, that we used to share some documents or share some kind of other visual as well as some kind of images. So all those kind of things we used to do by using this particular communication system. once you are having these ones, that this kind of recent communication, so what you are having later, that the most important thing in the communication or most important stuff in the communication is nothing but your electromagnetic spectrum. This electromagnetic, so what do we mean by electromagnetic spectrum? Well, it covers a very wide band or wide range of frequencies, and not only frequencies, it also covers a wide range of wavelengths too. So what you are having, that depending upon the number of, or depending upon the frequency value, the different ranges have been quantified, and always people used to go for their, people used to target some kind of high frequency applications. Why I am just coming within few minutes. And let me just tell you, in fact, those who are just beginner, who are at the second as well as third year, so you can see over here that this electromagnetic so here this is the scale of increase of the frequency. So at the lower frequency range, you are having the radio waves, and then you are having the microwaves, and then it will go to the optical region, followed by X-rays, gamma rays, etc. And whenever we are coming to the optical spectrum, it is not only the visible range, it will also cover some infrared radiation as well as the ultraviolet radiation also. So all of these are comprising together the particular electromagnetic spectrum. Now, all the spectrum has its distinct meanings as well as significances. So how to do that? So let me just tell you about the frequency bands. So I will just, this particular slide is for especially for those that who are at the BTech second and third year students, and especially who want to join some kind of core sectors after completing your bachelor's degree or your master's degree, even if someone of you are attending. So whenever, if you are choosing any kind of core companies, so they will ask for this kind of frequency band as well as their particular applications. The very first one is some few hertz to 10 kilohertz. This range is known as the audio frequency range, which is extensively used for the telephonic applications. The very next range is lying between 10 kilohertz to 30 kilohertz, known as VLF, or very low frequency applications, which has been employed or which has been incorporated towards the long distance communication. The next range is between 30 kilohertz to 300 kilohertz, known as the low frequency application, and which has been used for the navigation purpose. So what do we mean by navigation? Suppose if you know the coordinates of two places very accurately, okay, you can find out the coordinate of the third place. So what is the meaning of this one? Suppose you know that, well, you perhaps know that what is the exact coordinate system of, let us consider, since most of the attendees are from West Bengal as well as from Kolkata region, I am trying to emphasize like that way, that suppose if you are having, suppose you know the exact coordinate system of Shialda railway station, and also you know the exact coordinate system of Baruipur railway station. So you can find out from the calculation of these two what is the exact location of the of Swami Vivekananda Institute of Science and Technology. Okay, but what you have to know, you have to have the knowledge of at least two coordinates very accurately, and accordingly you can calculate what is the coordinate of the third one. The next one is the medium frequency, which is 300 kilohertz to 3 megahertz, and this has been extensively used for the radio broadcast. If you consider the conventional audio frequency range or conventional radio frequency range, if you just consider the conventional AM, if you just consider that, under that condition, you can consider that range frequency range that lies between 550 kilohertz to 1650 kilohertz. This is the exact frequency band of a of the radio transmission under AM signal. The next one goes for the 3 to 30 megahertz, and this comes with the high frequency application, and which has been used for the walkie-talkie applications. The very next one is between 30 to 300 megahertz, used for the very high frequency or VHF band. used for the television as well as for the frequency modulation application. If you notice very accurately, the FM frequency bands, they are in between, lying between 88 to 108 megahertz. Okay, if you just consider the Red FM or Big FM or Radio Mirchi, all of them are between that 88 to 108 megahertz. So those kind of things will you have to take into the account. The very next one is 300 megahertz to 3 gigahertz, which goes for the ultra high frequency or radar applications. Okay, and followed by that is the super high frequency or SHF, which has been used mostly for the satellite application. Then you may have 30 gigahertz to 300 gigahertz attributing towards the extra high frequency, which has been used for the defense radar application. And then you see that I am just making one gap. Why I am coming to that one later. 30 terahertz to 3000 terahertz, which attributes towards the optical range. Now here, these three frequency bands, that is encompassing 300 megahertz to 300 gigahertz, this frequency band, if you just compute the corresponding wavelength, you will find the wavelength is lying between 1 meter to 1 millimeter. Okay, and this particular frequency range that particularly corresponds towards the microwave frequency band, the original microwave frequency that lies between 300 megahertz to 300 gigahertz, and the corresponding wavelength is between 1 meter to 1 millimeter. Okay, so this is the complete usage of the frequency band. So I will just request that if the BTech students, second and third year, if you want to have this particular photograph, you can take it. Or should I continue, or you want to take the photograph? I can stop for a few seconds. So these ones I want to elaborate that these are the extensively used for different applications. This is the complete electromagnetic spectrum. In many of the cases, whensoever you will join in or you are going for interviews in many of the core sectors, you may be asked for this kind of frequency band applications. Now, mostly what I will do, I will concentrate towards the higher end, means this particular, the last 4 segments, I am concentrating on that one. So basically what is happening, whenever we are going for high frequency, well, these frequency bands of application means what? These are nothing but our carrier frequencies. You already know that in case of any kind of communication, you have some kind of baseband signal and you are having some kind of carrier signal. And why they are required? They are nothing but you need some kind of modulation, right? Now, once you are going for this kind of modulation, so what you do, that you basically have to translate the frequency accordingly, right, over the particular carrier frequency spectrum. And that you can do much easily by using or by employing this kind of frequency band, right? So basically what happens, so I should say over here that what are the basic components of a communication system. You already know the very first thing what you require is nothing but a source, and then you require a particular transmitter which basically goes for the modulation, okay, or which particularly takes care for the modulation. And then you require some kind of transmission medium so that the signal can be transmitted and it should be properly received at the receiving end, right? And then it should be properly transferred to the destination, right? So these are the 5 different components of a basic communication system, okay? Now, what do we want, or what are the basic salient features in a communication system, right? You already know that why do we need this kind of communication, or why do we need modulation? The main thing is you have to use that, or you have to realize the physical size of the antenna, right? Now, what do you have the antenna? It is of the order of lambda, right? So once you are going for high frequency region, then what you can do, you are basically incorporating lower lambda, which is much easier to incorporate in practice. And also what you can do, you can think for that you can handle much higher power, and also you can go for some kind of multiplexing applications. So all those things are feasible by using the basic communication blocks. And what are the distinct figure of merits in a communication system? The very first thing is the signal to noise ratio, or SNR. Okay. Now what you are having, the next one is the channel capacity. Well, now I try to just go back to the previous slide. If you just consider, I have told you that we need some kind of high frequency FC value, or the carrier frequency value. So what happens? The carrier frequency high means, as per the Carson's rule, the bandwidth requirement that will also get enhanced, because bandwidth requirement, it is nothing but 10% of FC. This is the thumb rule, right? So if your FC gets higher, so bandwidth requirement that will also get enhanced by a factor of 0.1. And what you are having that gives rise to, you already know there is a law which is known as Shannon law in a communication, C equal to B log to 1 plus SNR, right? So if your SNR, or signal to noise ratio, remains constant, so what you can think of, that if your FC increases or carrier frequency increases, you can have the enhancement of your bandwidth, which in turn gives you the more channel capacity. That means you are nothing but having more number of channels that can be embedded over a particular, or you can have a more number of signals that can be embedded over a channel, particular channel. And the another one is the noise figure, which is input SNR by output SNR. So what you require, that you should have in a system very high SNR, which gives rise to the noise figure that should be decreased as low as possible. So these are the few structures you want to have. Okay. Now I will come to our main agenda today, that is the high frequency communication. Mainly I will talk about the microwave as well as the optical communications. Okay, so in the microwave range there are three distinct applications. Okay, mobile, satellite. The third one I want to emphasize today, especially I want to explain that to my colleagues as well as my younger generations, because these particular applications, many of the persons who are even working in this field, they are not aware of. This is a radio astronomical applications. I will discuss in details today, and I will show you some images, some interesting images where I believe you will also find some of the interest. Also, and what we are also having, we basically go with the optical communications also at the higher frequency range. And in between the two, if you can notice, I had ended up while showing the electromagnetic spectrum at 300 gigahertz. Okay, and what I have told, the next range was starting from 30 terahertz. So you are having a gap between 0.3 terahertz to 300 terahertz, and in between these two, you are having a bridge, and this bridge is basically giving rise to some kind of terahertz gap or terahertz domain. I will also speak about something about this one also in today's particular presentation. So to begin with, that how this particular microwave communication has come up with. The other day, Professor Chinmoy Saha had explained a lot about the microwave or electromagnetics environment. I will tell about some kind of other things, that I will say that how the wireless communications have evolved. And these three figures, in fact, I think that all the students, all of you already aware of the names of all these three people. Okay, the first person, that after which the unit of frequency has been named, then Sir J.C. Bose. Okay, and then we are having the Marconi, who had bagged the Nobel Prize due to his ability to show the demonstration of the wireless communication from one continent to other. So here I am showing you the pictures, some of the images. By here you can see the left one, that where Sir J.C. Bose is demonstrating the particular experiment, where he is demonstrating the short wave transmission, okay, between the transmitter and the receiver at Royal Society London. And I'm telling you that all this experiment has been extensively carried out in India, and more particularly in Kolkata itself. So this is this is the beauty of the experiment. So the first, that so-called Make in India project that was evolved at those times. And the right one, I'm showing you that this particular figure, that where here are the some kind of towers which has been used by Marconi while demonstrating the free space communication of the wireless signals in early 1900s. Okay, so what you are having that, in fact, you know that when J.C. Bose had carried out all these works, okay, in Kolkata in Presidency College, he had not claimed any kind of patent, okay, and due to which, you know, that he had not, he thought that, well, that let me be very, in fact, this is my own idea, this is my amateur things, and hence he didn't call for any kind of other things. So his work was got, you know, that he didn't go for any kind of further works regarding that one, and hence he was deprived for this Nobel Prize here. But later, you know, if you see this particular figure, what I am having, that if you see the title of this one, the importance of J.C. Bose for the 100 years of millimeter wave research. Okay, nowadays everyone is talking of the millimeter wave communication, okay, 5G. The first one who had invoked this is nothing but J.C. Bose. If you see the publication, it was in 1997. The just previous figure, if I just go back, it was in 1897, and this one is 1997, just 100 years later. Okay, and this is one of the, you know, that one of the very, very prestigious conference in the area of microwave domain, which is known as IMS, or International Microwave Symposium. In each year, it is held in US or Canada. Okay, so this here, this particular one, this, you just see the title, this paper, this is nothing but a simple homage to the contribution of J.C. Bose. And what has been done later, our press, in fact, they had also highlighted his effort, and you can see this is a newspaper cutout from 2012, where the US agency is nothing but IEEE, who had made some kind of they honored the role of J.C. Bose and C.V. Raman, who had carried out their extensive research in India, especially again in Kolkata. And here I am sharing you the plaque, which has been given by IEEE in 2012 to Kolkata. And if you just read it from there, it's fine. And if you can see over here, this was what has been written, that Jagadish Chandra Bose in 1895 first demonstrated at Presidency College, Calcutta, India, transmission and reception of electromagnetic waves at 60 gigahertz, okay, over a distance of 23 meters through two intervening walls by remotely ringing a bell and detonating gunpowder. For his communication system, Bose developed early millimeter wave components such as a spark transmitter, coherent dielectric lens, polarizer, horn antenna, and cylindrical diffraction grating. So all of them have been made by Sir J.C. Bose himself. He had not purchased or procured any item from market. He had developed everything by himself. So IEEE had given some kind of, honorarium contribution to due to his big contribution in this particular area. Later, this kind of application has also find some kind of areas like satellite communications. What you need, you have some kind of satellite in space, and here you are having one transmitter, and here you are having some receiver. So some wave has been launched from the transmitting antenna, which has been received by the satellite and which has been processed and transmitted back towards the ground earth station. Okay, and here some kind of important satellites. The first satellite which has been launched in space is Sputnik 1 in 1957, and later Intelsat was launched in 1965, and within a very few years, the first satellite which has been launched by Indian team was Aryabhatta in 1975. And this particular Aryabhatta launch has been, everything had been done by this gentleman, who is nothing but the father of Indian space research, known as Dr. Vikram Sarabhai. Okay, so he has made all the initiative. In fact, he had basically developed the organizations like ISRO. Okay, so all these activities had been started by him. And here I am showing you some of the important satellites which has been placed in space. So the very first one is LEOS, or low Earth orbiting satellite. An example may be our GPS satellites. The next one is MEOS, or medium Earth orbiting satellites. So one example is our Indian remote sensing satellites, or IRS satellites. And then we are having the geostationary satellites, or GEOS. We are having the Indian National Satellite Systems, or INSAT satellites, which has been used for some kind of multi-purpose applications. Okay, you may have some kind of telemetric applications, some broadcast applications, some meteorological applications, and etc. Okay, so what we are having, that how the satellites are launched in space, you know that these are some kind of initial ones. You are having that over the Earth, the satellites are rotated over here, and when the satellite is very close to perigee, they had been applied some kick so that they are going to this particular one in apogee, and again it has been applied to some other kick so that they had been means initially from low orbiting, they are then making this kind of transmission so that you are having some kind of transfer orbit, and accordingly it is going towards a final geostationary orbit. So all of these things are getting together. So this is the simple thing of launching of a satellite in space. And in any case of microwave devices or satellite application, one of the very important component is antenna. And in a transmitter and receiver, these antennas play an integral role. So what you are having, so if you are having two antennas, and if you are having the power received at a receiver is PRX, and if the power transmitted by the antenna is PTX, then one can show by using Friis equation that PRX equal to PTX, GTX, GRX lambda by 4 pi r whole square, where I have just mentioned over there what are their respective meanings. Okay, and here one of the very important components in antenna environment or antennatic terminology is the effective isotropic radiated power, or EIRP. So PTX, GTX, if you can multiply and take a logarithm of that one, so you can get what is the value of EIRP in dB. Okay, so this is very, very important one. Then I am coming to the another important application, which is radar, or radio detection and ranging. So what you are having some distinct target. So what you are having from the transmitter side, you are basically applying some kind of transmitting pulse, which is going and hitting the target. And from the reflected one, what you can do, you can characterize what is the symbol or what is the meaning of the target cross section, or what are the characteristics of the particular object. So all those things can be detected by using these ones. And what are the different observables, like target range, target angles, target size, target speed, and target features. So all of these things can be carried out by using the radar environment. Okay, so these are some of the applications over here of the radars. And here I am also showing some of the distinct radar frequency bands you can see between L to Ka, and here the particular wavelengths have also been mentioned. So these are the particular frequency band L, S, C, X, Ku, K, Ka, ranging from 1 to 2, 2 to 4, 4 to 8, 8 to 12, 12 to 18, 18 to 26.5, and 26.5 to 40 gigahertz respectively. What you are having, why these names have been given, you know that the radar has been invented or invented during the time of World War II. So just these names have been given so that one can identify or one can distinguish their names from each other. So those kind of things, just to use some kind of code language so that the enemy radar cannot be detected. The enemy cannot detect your own radar. So those kind of things have been done for the, you know, for the names and coding had been done during those days, which has been taken by IEEE and later has been used for the later microwave communication purpose. And here I am showing you one of the just strip that one particular diagram how you can detect the target by using radar. Okay, some kind of simple range measurement system. Okay, and the radar signals, while propagating through the atmosphere, okay, it has been getting perturbed by a number of environmental influence like atmospheric attenuation or reflection from this Earth's surface, over the horizon diffraction, as well as the atmospheric refraction. So all those things that that when the signals are coming from a distinct object, so all these particular effects are coming into the picture, and your received signal will get affected. And what is the way out? So whenever you are receiving the signals, you can go, or you can think for that, well, that I have received the signal, let me go with this one, or let me analyze by keeping into the mind, well, it has been undergoing some kind, all these effects, and accordingly the channel modeling should be done and things should be performed. Okay, so these are some kind of radars usage, okay, like remote sensing, geographical applications, some wearable radar, air traffic control, okay, weather radar. So there are many applications of radar. Now what I want to mention, this is the most important part of the story, that which I want to show or want to demonstrate to my younger colleagues, that this is application towards the radio astronomy. So what do we mean by radio astronomy? Well, if you see our atmosphere, okay, how does it look like at different frequency range? Well, you concentrate over here, you can see over here, you are having an opaque atmosphere, and here there are certain windows over here in optical range, infrared range, okay, and here you are having a very high window in the radio wavelength range, okay, while you are again not having any kind of window at a lower frequency. If you see over here, because as the wavelength increases, that means you are having the lowering of frequency. But in the what you are having, that at this range, if you see over here in the microwave frequency range, you are having a large window, right? So that's why that people used to observe the stars, that how the distinct objects will look like at the high frequency region. So what you are having, so basically radio astronomy, it is nothing but the study of the universe at the radio wavelengths, okay? And what you may have over here, that it was first started in 1930 as an offshoot of the developments in the radio communications technology. I am coming to that story for that within very few minutes, okay? How does that evolve, okay? Now what is happening, that if you go forward, so basically what do we mean by astronomy? Astronomy is nothing but, astron means star, okay, and nomos mean law. So basically nothing but laws of stars, or study of the celestial objects, okay. So what has done, that nothing but the studies have been done for a distinct radiation which is coming from a distinct stars, okay, and accordingly it has been analyzed, okay, in the particular domain. I am telling you, there was a very renowned scientist, all of you have heard his name. His name is Professor Meghnad Saha, who had first talked about the absorption and emission spectrum. And from that one can show that how this sun's outer shell or sun's peripheral that consists of the hydrogen and helium, okay. So basically what happens, that it corresponds to each and every element, you are having a distinct lines, okay, and once you are receiving or once you are observing the particular radiation at different frequency domain, you can find out, well, I'm supposed to get suppose I'm just giving you one example, but if you have a radiation from element X, you are getting or you should get an absorption spectrum at frequency F1 and F2. Suppose I'm giving one example. If something is coming from Y, you are supposed to get at F3, and if something is coming from Z, you are supposed to get at frequency F4, right? Now suppose you are observing a particular object and you are getting absorption lines at F1, F2, and F4. What does it mean? This essentially means very simple. The essentially meaning is the particular radiation that consists of the elements X, because X corresponds to radiation of F1 and F2, and then it also consists of the element Z, because it consists of the radiation at the frequency F4. Okay, so all those both the things have been taken into account. Now the astronomy, it has been studied at different wavelengths, as I have told you. So you can study at gamma ray region, or at the that infrared region, or X-ray region, or UV region, or optical astronomical region, that is our visible spectrum, 400 to 700 nanometer. Now if you see about the astronomy, if you whatever you have studied till date, you know that you need a telescope. Why? So that you can view the object. Now what is happening, that if you consider the visible spectrum range, that lies between 400 to 700 nanometer, right? And what we are having, that everyone, or every that all of our pupil, they consist of a visible filter. So every one of us can see that what is the whatever we are seeing, that everyone we can see the that physically they are same, right? Suppose if someone asks you that how Somak Bhattacharyya looks like, and if he does not know me, okay, if you explain to someone, so what he can do, he will very easily, he will understand. How? Because both of you are having the visible filter at your end, right? But what you are having, that if you are going with, if you don't have the visible filter at our eye, then all these realizations will be different. How? I'm coming to that point very short. So what I am showing over here, that the universe at different frequency range, I am showing you the particular realization of our universe at different frequencies. So you can see some objects, like you can see some nebula which has been measured in the optical domain, then this gamma ray survey of our sky, then one of the Cassiopeia 8, that is one which has been studied in X-ray domain, then in the same galaxy which has been studied in optical as well as in infrared domain, and you can see the UV representation of another galaxy. So everything have been used over here. So what you can see, that there is no correlation, means you need some kind of this kind, you can make beautiful images of all these objects. Now what I was just discussing, that about the particular radiation, I want to make my video on for a few seconds, my camera on, just to explain one thing very clearly. Am I visible? One of you please tell me, am I visible?
Yes, sir.
Okay. Yes, sir.
Okay. So if you see that, for example, if suppose that one radiation is coming from this end, okay, this is an astronomical object, and this is rotating around its own axis, right? It is certain rotating, and from this end, just recall the radiation is coming out, right? So what is happening? Suppose this is coming out over here. Here the observer means towards the screen, the observer has been placed. So now you will receive radiation. It is going like this, spinning again around the orbit. Again, it is coming over here. Again, you will receive the radiation. Okay. So what you are having, that after certain intervals of time, you will receive some kind of radiation. Now, I'm sorry that, yeah. So if you see this particular figure, so here this particular scientist, his name was Carl Jansky, after which one unit has been named in astronomical science, which is known as Jansky. So what has been done, that he was trying to make, he was a radio engineer, and he was going to try to measure some, detect some signals. And what he was getting, that after a certain interval of time, certain radiation is getting repeated. If you see over here, you are getting some radiation over here, here, and they are coming just after a certain interval of time. So this one, whatever he is receiving, this is nothing but whatever the object I was just showing you, that is known as a rotating neutron star. Okay, a very fast rotating object. So he was getting the radiation from that one. Okay, and from this one, from once he had made the discovery, so this particular domain, people used to, people used to think for that, well, at the microwave frequency region also, that people can think for this kind of applications or some kind of radiation. So once he has done this one, so what has been done later, that the radio astronomical things, it has been also started in India also. Now, well, this particular antenna, whatever you are seeing over here, this is the Jodrell Bank radio telescope in Manchester, okay? And the particular person that whom you can see at the inset, okay, his name, I will just come to his name, okay? And what he has done, he was first made this kind of imaging of an object which you can see over here, and later when the resolution gets improved, okay, people had made this kind of beautiful images, okay? So what is the meaning of these two? So once you are having these ones, so what you can have, you can see, so this experiment, whatever he has carried out, this has been done in the 1960s, okay? I think Professor Sarkar already may have known his name. He's nothing but one of our professors, Professor Mrinal Kanti Dasgupta or N.K. Dasgupta from University of Calcutta Radio Physics Department, okay? And he had carried out all these calculations by sitting at our department over here. I am showing you one of the snaps of Radio Physics Department, okay, in Calcutta University, taken by me long ago. So what has been done, that here the two objects which has been done over here, and the resolutions can obviously made it better, that once you will go with the, you know, that resolution you can think of, that is lambda by d, okay, where d is nothing but the, you can think of the aperture distance. So by improving the aperture, the resolution can make much better. So later the second figure has been come out, okay, by making the resolution better. And so what is the main contribution of him during 1960s? You can see that wherever he is locating or he is predicting about the particular object's image, that is very, very good, very, very accurate in those times, okay. So I am also showing you some of the telescopes earlier that which has been used for the other frequency domains like ultraviolet range 1978. This has been Subaru telescope in Hawaii. And in space, there is one telescope which is known as Hubble telescope. Okay, it meets the infrared domain of applications or observations in 1990. It has been launched in space at 600 kilometers above the Earth's surface. Here, I am showing you a particular block diagram of a typical block diagram of an antenna in a particular radio astronomical observation. So this particular antenna, don't get any kind of confused. This is nothing but your super heterodyne receiver, which you have already used for the AM signal demodulation, right? It is similar to that one. So what you are having, that any kind of distance from distant object, any wave that is striking the particular, you know, the aperture of the primary receiver, and then it is getting focused at the secondary receiver over here, and then connected, and then it has been processed in the other end. Okay, so this is a typical arrangement of a radio telescope. Okay, and here I am showing you the front end of a particular receiver, as I have just told you. So you are having some kind of feed over here, and then you are basically making the particular signal that you are making in the two orthogonal polarizations, and this has been multiplied by a local noise amplifier. Okay, and then you are mixing it by using a local oscillator signal, and then by having the IF amplifier, you are processing it. So all these things have been done in the receiver system itself. You can see this block diagram. This is very, very much similar to the super heterodyne receiver, which you have already studied for the amplitude demodulation case, right? Now what you are having, this one, that here I am showing you the single radio dish telescope, okay, which has been used for the one which has been used for the radio frequency application or radio astronomical application. This is the first one, which is Arecibo, Puerto Rico, the largest one. Okay, and later another one which has been come out in India. India was not far behind. So they had also come out with a very beautiful single dish radio telescope. Well, you may argue with me, sir, here you are having multiple one, but no. What you are having around a single axis. You can think of that they are nothing but you are making the baseline larger. Okay, so this is the radio telescope which is built near to Ooty. It is known as Ooty Radio Telescope or ORT. It is 530 meter long, 30 meter wide, and operating at a frequency of 326.5 megahertz. Okay, so these are some kind of things of the radio which is a single dish radio telescope. Well, whatever we have considered. But suppose I want to make, the 1 kilometer long distance. Okay, can we make it physically? we can't make it, right? So what people have thought of, some kind of array telescopes. So what do we mean by antenna array? Well, you are having a number of identical antennas. They have been arranged maybe in some particular configuration, and what essentially it does, it essentially enhances, okay, the particular aperture size. And basically what happens, as I have mentioned just few minutes ago, the resolution, it will get improved because the sensitivity, it is a function of this aperture size, okay? Because as the aperture size increases, that is d increases, your lambda is fixed, so lambda by d, that will decrease, right? So lambda by decreases means what? That your resolution will get enhanced, okay? And why what people can make, that people can make that, well, if you have a single dish, okay, which is of the order of 100 meter, even if you have a fully steerable one, it is very difficult to build, okay? And so people always go for this kind of, that some kind of array telescopes, that which is much easier to build and much easier to control, that people had gone for those kind of applications, okay? So once this has been come out, so what is the main thing? Another problem, that is the, well, you have made some kind of array telescopes, very good. Now suppose you are making array in a single line, right? But what will happen? Earth is rotating, right? So when the, that, again, let me just 1 second. Yeah. Again, let me make my camera on. Just tell me when you are, am I visible? Am I visible? Yeah, yeah.
Yes,
Yes, sir. Yes, sir. You are visible, sir.
Okay. Suppose this is the object. Okay. So from here, this one is coming, and suppose we are having the two antennas like this way, or maybe a number of antennas like this way, which is the baseline like here. Okay. So when the Earth is rotating, right? So at a particular instant of time, maybe it is looking like this way towards the object, right? Now in the next moment, it may have since the Earth is rotating, it will project a baseline like this way, right? So what will happen? The baseline is getting a function of time, right? So what will happen? So what I have to do? So as the baseline is getting the function of time, so what will happen? Your resolution, that will also become a function of time, right? So since this have to be done, so what you have to make? You have to make an antenna array in such a way so that it will cover some kind of uniform area. And so what has been done? So people have come out with some kind of Y shape. What is the significance of Y shape? Just you think of a particular fan, okay? It will have 3 blades, right? All our ceiling fan has 3 blades. Why? So that with the minimum number of hands, you can cover the maximum area, right? So 3, similarly like a Y configuration with 120-degree apart, so you can cover the maximum area. So this one, what has been done, that here I am showing you some kind of array telescopes all over the world, some of the important array telescopes like Merlin in UK, then in Chile, it is Atacama, okay, in Astron, it is in Netherlands. We are having very large array or VLA in New Mexico. By the way, Professor Dasgupta's contribution, which I have shown you just few minutes ago, later when the image was improved, it has been improved by using this VLA or very large array in New Mexico. And also you are having the low frequency array or LOFAR, which has comprised between the 4 different countries like UK, France, Germany, and Netherlands. Okay, so here I am showing you some of the antenna arrays. Okay, and what we are having, our India, that is also not far behind. We had the GMRT telescopes, or giant meter wave radio telescope. Okay, and this has been come under TIFR, or Tata Institute of Fundamental Research. Here I am showing you some of the central arrays of of this GMRT, and here some of the views. Again, I am showing over here the GMRT telescopes. Okay, here you can see a number of antenna arrays. Okay, so these are nothing but the individual antennas. I am showing you this particular picture. This has been taken from one of the plateau region over there. Okay, and this particular gentleman whom you can see over here, he is nothing but the father of radio astronomy in India. His name is Professor Govind Sarup, and He is now 91 plus, resides in Pune, okay? And well, many of us don't know his name. That is quite obvious. I will just suggest you, younger generation, again, please Google his name. You will come across to know much better about him, okay, very soon. And what you can do that, I can tell you that Professor Swarup, how big he is. Just see this particular one. A journal which particularly dedicates his contribution in the Indian radio astronomy. And you know that this GMRT facility of Tata Institute of Fundamental Research, this has been completely again done by Professor Swarup by having the complete Indian technology Make in India project, okay, so-called Make in India project. And what he has done, you know that he was, at that time, he was working in Stanford University in US. At that time, the TIFR director was no other than Dr. Homi Jahangir Bhabha. All of us have heard his name. And Dr. Bhabha had written a letter, okay, so that Professor Swarup can join over here in GMRT. I will just ask you people that this article is available in web as open access. Please read this article. You will get a lot of, this is a simple general article. You don't need to have much knowledge about, you know, many technical things, but you will learn many things about Professor Swarup while reading this particular article. And if you see this one, that this has been published in 2019, and when you can see the date 23rd March 2019, which was nothing but the 90th birthday of Professor Swarup, okay? And you know that I know many stories of him, not only from this particular article, but also from listening to him while I was in GMRT, while doing my master's thesis and later. And well, if you don't believe me, you can see this, okay? This is me with, well, if you have not noticed me carefully, this is me standing with Professor Swarup at different locations. This was in 2011 in IIT Kanpur. I was a PhD student at that time. This was my visit in TIFR Pune, NCRA TIFR Pune in 2013 in this office, okay, that in the, you know, that at the reception desk. It is at his home in 2016 where I got the opportunity to visit him. And last year also I got the opportunity to meet him just before his 90th birthday in 23rd March 2019, just few days before in APRAS, Asia Pacific Radio Science Conference, took place in New Delhi in 2019. So I got the opportunity to meet him in all this time. Yeah. So Professor Swarup, yeah, he's a, you know that if you just talk with him and you will come to know a lot of things while discussing with him. But yes, I don't know that how much active he is now because he's already 91 plus. Just we have to take care of that one also. And let me just show you, these are the some kind of details of GMRT. As I have told you that it's a Y-shaped antenna. So you can see over here, which is encompassing a region of this, the radius is something around 25 kilometers. You are having some 30 antenna dish, okay? Here I am showing you some of the receivers of GMRT. This is in the twilight, okay, and one of the receivers of GMRT I'm showing over here. And also I can show something else, that I can show that how this one is very important, that well, you can have the radio imaging, some kind of other applications like GPS satellites, spacecraft navigation, some medical imaging where you can have the CAT scan or some kind of coronal mass ejection from sun. All those ones are the nothing but some of the applications of the radio imaging, okay? What we can also have, that why this is very important, imaging of a source is very, very important. I am just showing you that a Crab nebula, you can have the observations at different frequency range. And different frequency ranges, how? X-ray, optical, infrared, and radio. What you can see, is there any kind of correlation? I don't find any. So what I had told you earlier, just if you just recall, that visible, if someone asks you how Somak Bhattacharyya look like, so you can tell it very easily, right? Because another person can also detect that one. But here, if you see that if you ask someone that how the Crab nebula looks like, okay, because here then under that condition one can only see in the upper left one, but sorry, upper right one. But in this one, in the radio domain or IR domain or in the X-ray domain, its projection or its imaging is simply different. You don't have any kind of correlation between them. And here I can show you our own imaging of our own Milky Way. So what you can see over here, that the Milky Way had been, that this has been imaged or this has been analyzed at distinct frequency ranges, and they are having again no correlation with each other. So what you require the imaging at each and every frequency range. That is very, very important. Okay. And I am coming to the next one as the optical communication one. So what you can have here also the transmitter receiver or you are having, and here you are having an optical transmitter like a laser where you can send some kind of optical pulses. Here you are having some repeaters so that signal gets regenerated. And again, the light pulses, it is just propagating through a fiber optic cable, and it is detectable at the receiver end by having some kind of photodetectors. Okay. So here I can show you the optical fiber, what you are having. Once you can see this particular one, so what you are having, that in this case, you are having a certain attenuation. If you see that at 15.50 nanometer on 1.55 micron, if you see the characteristic graph, here you can observe the minimum attenuation, and how much it is 0.2 dB per kilometer. It is specified. Okay. Now what is happening? So suppose you want to send some signal over some higher kilometers. So what will happen with the progress of the kilometers or progress of the distance? The signals will get attenuated. And so what is the way out if you go with the optical one? Well, people had come out with a beautiful idea. The solution is RF over fiber. The radio frequency that propagates either through a waveguide, you have studied already in your second or third year, and also you have seen that radio wave that also propagates over the free space, right? But here, through the optical fiber, you can send the radio frequency. So what you can do, you can modulate the signal properly, and you can send it through an optical fiber. So I am showing you that some of the applications are that, like some kind of broadband mobile communication, where you can have some low noise figure, low insertion loss, high power achievement, and this gives rise to the increased number of subscribers. Okay. Also, what you can have, you can generate some millimeter wave signals for local oscillators in radio astronomy, because you need a radio astronomical observations, you need a local oscillator signal to that, so that you can make proper mixing to segregate the IF signal, right? And also you need some kind of like satellite earth station remote antenna application. I can show you one of the interesting one in optical communication. One of the important application is like wavelength division multiplexing. So I think that you have studied the basics of analog communication, where you have go with TDM or FDM. So it is like the same. So here you can generate, you are having the single longitudinal mode laser, so it will resonate only at a particular frequency, so or a particular wavelength, whatever it is. Suppose it is resonating at lambda1, lambda2, lambda3. You are having the multiplexing. You are sending all those signals through a particular optical fiber as well as amplifier configuration. And here you are having the receiver, which are basically receiving the signals at the transmitted at lambda1, lambda2, and lambda3 respectively. Okay. So this is the WDM or wavelength division multiplexing signals. And when these lambdas are very close, okay, lambda1, lambda2, lambda3, if they are very close to each other, that gives rise to DWDM or dense wavelength division multiplexing. So I am just showing you one of the applications of DWDM over here in GMRT. So here you can have a transmitter. This consists of the lasers. Okay. Here you can have a receiver, which consists of the photodiodes. And here you can have the four channel. You can see the five distinct channels of multiplexers and 5 distinct channels of demultiplexer. Okay. So 5 channels can be, that they can be transmitted simultaneously over a particular wavelength, okay, or for a particular channel. Okay. And here I am showing you that how wavelength division multiplexing had come out into the picture in upgraded GMRT system. So as I have told you that in a radio astronomical system, you are receiving the signal in two orthogonal polarizations, and since they are basically orthogonal to each other, they can't mix with each other or can't interact with each other. And then what you can do, you can make some kind of pre-amplification of those signals, okay? And then you are splitting the signals by a 3 dB. That means nothing but a power splitter of half power. You are making half of them for the IF frequency, and what you are doing, the rest of the power, again you are feeding at the feeding by using some kind of amplifier, and you are feeding at the two distinct receivers. Okay, I'm just naming them OTX1 and OTX2 just to signify that they are nothing but the two distinct receivers, two distinct transmitters. Okay, so here you are making, this is toward the transmitter end, and you are having the DWDM multiplexer over here, and it is propagating through the optical fiber, and again at the receiver end they are getting generated or received it, and then they have been received out here over here, separating out by using two different receivers, ORX1 and ORX2. Okay, what you can do, that this system, this can also, but well, you have designed it, but you should also make sure that it should support the existing one. So what people have come out, if you see that, as I have mentioned, that 1550 nanometer, this corresponds to minimum attenuation. But the previous one, it was working at 1310 nanometer. So what has been done, if you see the IF signal, it was operated at 1310 nanometer. So what has been done, 1310 nanometer is coming from this end to this end, while 5050 nanometer, that goes from this end to this end. So what you can have, the IF signal that can, since they are operating at two distinct frequency ranges, so that means you cannot have any kind of interference with respect to each other. So this is the one with the support with the existing link of GMRT. And whenever you are doing any kind of observations, another very important point that comes into the account, which is known as the third order intercept point. So what you are having, suppose you are having two fundamental frequencies which are very close to each other, that is F1 and F2. Okay, and what you are doing, you are basically going on increasing their power. And what you are doing, first of all, you think of that you are mixing the two signals, F1 and F2, and once you are mixing, well, a kind of mixer means what you can think of, well, there may be multiplier, right? But what you can have, if you consider a practical mixer, instead of having the linear combination, you will also get the nonlinear combinations of the higher orders also. So with the nonlinear combinations of higher order, what you can have, there are intercept from the two significant frequencies. So here what you can see over here from this graph, that well, your original one, that is getting increased like this way, this is the slope of the original one. But if you increase the power, then the third harmonic, that particular power, that will go on increasing like this way. So what is the values of the third harmonics in this case? They are nothing but 2f1 minus f2 and 2f2 minus f1. Let me just try to explain it by a simple example, which will be easier for you to understand. Suppose that this is the experimental characterization to determine the 3 dB, the 3 dB, the third order intercept point. So with the signal generator 1 and signal generator 2, you are generating two distinct frequencies, F1 and F2, which are 500 megahertz and 501 megahertz respectively. So if you calculate 2f1 minus f2, it will be 499, the other one will be 502. And here the combiner, basically that gives rise nothing but that you are combining the two, mixing the two signals, right? And then you are amplifying the signal, and this is nothing but an optical transmitter. And through this one, you are having some kind of communication channel or optical fiber. It has been received over here, and you are basically visualizing the IF signal over here in the spectrum analyzer. So how you will do that? Well, if you just think with this one, this is a spectrum analyzer. So if you see this one, if you see this M1 and M2, they have been located, if you see these ones, so they have been located at the two frequency points of 500 and 501, very close to 501. And these two, 499 and 502, if you just notice what you are having some kind of significant power, right? Now, this one is very, very important, or very, very crucial in the radio astronomical observations. Whenever you are making some kind of, that object is coming from a very distant space, okay, and the distance is, some thousands of kilometers from where the particular the radiation is received. So whenever it is coming, so just you think of the signal which has been received by your antenna at the Earth station. The signal is very feeble in nature, right? And once you are trying to, trying to process the signal by some certain amplification and others, and suddenly you are mixing and you are come out with this kind of interference. So this is nothing but known as the RFI, or radio frequency interference signal. And third order intercept point is extremely crucial for this one. So what you can do, if you can make this certain arrangement, you can see that over here a certain range, the third order intercept, the third order harmonic is increasing like this way, and here this one, the fundamental frequencies are increasing like this way, and they are interfering at a particular point close to this one. So third order intercept point, you can easily calculate where both the straight lines will intercept at a particular input frequency, which is known as the third order intercept point. Okay, so what you have to do, the basic thumb rule is you have to that operate much below the power which has been characterized by the third order intercept point. Okay, now what you can do, that RF over fiber experiment, this has been also carried out in GMRT antennas. So this was me I think some 12 years ago in one of the antennas which is known by the name is W4 antenna. It is something around 15 to 16 kilometers away from GMRT. So what you can do, that how we can see that we can show the signal is perfect. So once the signal has been fed at this end, we have received, or one can receive the signal at the receiver end. You can see that here you are getting a peak at 500 megahertz. If you see over here that 500 megahertz, you are getting a power of 1.22 dBm, and over here that this is the noise level, that which is corresponding to minus 64 to 65 dBm. So what you are having, you are showing a distinct power which has been received by the antenna which has been placed far apart from there. I want to make a few highlight about the terahertz. So as I have told you, 0.3 to 30 terahertz, this is the terahertz gap. So what you can have, that you can make the bridge between the two, between electronics and optics. And what you can have, that this is basically at the same time the most exciting one as well as the most frustrating one, because the availability of the proper source or detector has been missing. And what you can have, that if you see the 1 terahertz, that corresponds to some 300 micron, and the associated energy with that one, if you do with hc by lambda, that is something 4.1 milli-electron volt. So what you can have, the associated energy is much less, and that gives you a much better, much better application, because you can have the ionization which will be much reduced, and that gives you some kind of security applications. For example, that over here in this particular bag, that some gun has been hidden over here, that can be easily detectable, and this particular person is carrying some knife, okay, that beneath the newspaper, which is also easily detectable. Okay, so what you can do, that by some kind of security by some security applications, you can do much easier ones by using the terahertz ones. So why I have shown you all these ones, because with this frequency design, that as I have told you, that with the gigahertz, terahertz optical one, people are very, very interested, because you can do a number of applications by making by using these frequency bands. So what you can do, that once you can do these multiple applications, so we need certain devices, and so you need certain antennas also. So here I am showing one of the antennas which has been generated in the terahertz range. Okay, and one can see the multiband applications of an antenna over here. Okay, and these are certain the gain pattern of the antenna one can visualize. Okay, and these are the what I want to say over here, why I am showing this particular slide, because this is the work carried out by 2 students, especially the first one, mostly he has carried out the work. The second one also worked hard, and with one of my PhD students. So what has been done, that they had carried out all this research in a span of 1.5 months only. and they have come out with a very good results, which has been published in earlier this year. And also people from other part of country visited us from, they have visited from places from Kerala Government Engineering College, and they had come out with some kind of wearable antenna design, okay. And here some kind of Yagi antenna, wearable antenna they had designed at some multiple band applications. And also that they had also gone for some kind of high frequency applications, which has been some kind of other applications, again by using some kind of artificial substrate or artificial magnetic conductors, okay. And they had also come out with a multiple band applications, and they had made some kind of certain improvements over here. And what one can also see that another one structure has come out, okay, that where one can again go with some kind of wearable applications again by using some frequency selective surface, okay. And here it has been designed in the gigahertz range. And what you can see that if you see that, what you know that you don't want any kind of radiation towards the body. So if you see the spectrum over here, so over here you see the back lobe that has been significantly reduced, okay. So this is the main application of the particular antenna applications, okay, that where the back lobes can also be reduced. And also some students again they have come out and they had done some kind of application in the high frequency as some kind of band stop filter application, as well as some band pass filter applications. So they have carried out some kind of results, and all this work I'm telling you that people have carried out in a span of 1.5 months only, 1.5 to 2 months, okay. So they had really worked hard during the aforementioned period, okay. And also I want to show that some student has carried out some kind of design to get some kind of polarization conversion in the terahertz region, okay. So you can see these spectrums. If you are interested, you can go through these papers, okay, which has been published. I am not explaining in details, okay. And also that some student has also come out with some kind of polarization conversion application, again in the terahertz domain, okay. And here I am showing the polarization conversion ratio, the graph. So what you can get that over a wide range of frequency, that here you can get a significant polarization conversion. So if I want to summarize in short, that what we can have, that plenty of applications are there that which you can one can carry out that in the high frequency region. And why it is very important, because you can exploit the higher bandwidth over here so that you can have more number of subscribers, okay. And here I am showing, I must show, because whatever the research work I have shown over the last 4 or 5 slides, this has been mostly carried out by these summer interns who have visited us in 2018 and 19. And people from the host institute, I think you know these two fellows, okay, Aprotim and Dipayan. They visited us last year, and they had carried out this particular research, okay, over here, and they had done very good one, okay. And here I'm showing you that some of the students that we had visited from other institutes, okay. And also what I want to show you, that I want to acknowledge that my students that who had devoted a much longer time over here, and we had got some funding from DST SERB, Government of India Science and Engineering Research Board, as well as from the IIT BHU authority itself. And here I am showing you some of the students that who have done. Suppose he has just started his masters with me, Shuman. He is Anango. He had also started his masters with me. He had recently graduated, Manikan. She graduated last year, Smriti. He also graduated last year, Aman. He is pursuing his PhD very close to his thesis submission, Vinit. He is Shombit. He is pursuing his PhD. He is Nilotpal, pursuing his PhD. He is Dipti Ranjan, pursuing his PhD. Vinit, he is graduated in 2018. Okay, the very first MTech student graduated with me. And he is Lovesh. The next one, the corner one, is Lovesh, that who had graduated with me last year. And I also want to acknowledge my collaborators that with whom I had worked over the last few years. So Professor P. Chakravarti, he is currently the director of IIST Shivpur. Also, Professor P.K. Jain, he's the director of NIT Patna. So I'm really happy to have strong collaboration with them, as well as with Professor Akhilesh Bhattacharyya, that he's in Penn State University in US. Okay, and I am having a strong collaboration with Dr. Santanu Das of my own institute in ceramic engineering department. Dr. Chinmoy Saha, perhaps the students who were present during the last webinar prior to Amphan that you were able to listen from him. He had given a very beautiful lecture, okay, on the electromagnetics teaching. And the next one, all of you know, the host of today's one and the most supporting people behind all of us, Dr. Chittojit Sarkar. I used to call him Chittoda, my senior in Calcutta University Radio Physics Department. And the next one is Dr. Smriti Dwivedi, my own departmental colleague. So we are having some good collaborations among us. And here I want to show again my campus in IIT BHU, the aerial view of the beautiful Vishwanath temple, which is situated within the campus. This is not the famous Vishwanath temple of Banaras. This is the VT of the campus itself. We used to call it VT corner. Okay, so this is a beautiful one. Once you will be here, we will be very happy to host you over here. And thank you very much for your kind attention. Thanks.
Thank you, sir. Thank you so much.
Thank you. Yeah, I am open for questions here.
Yes, sir. I have three questions, primarily from radio telescopy.
Yeah.
Sir, first thing, suppose there is a pulsar a few million light years away.
Okay.
Suppose it emits a specific radio, it emits radio waves at a particular frequency. Now, while it comes, it may experience some kind of gravitational redshift and
Right.
lensing and a lot of things.
Right.
So,
right. Completely right. Yeah.
sir, so how do we detect that it is specifically coming from a pulsar in that specific region? Because
Okay.
lensing and redshift definitely changes the frequency.
Yes, it will shift the frequency, but I am telling you that what happens. Well, first of all, let me tell you, I am not a radio astronomer. Okay, what I have
Okay,
tried
sir.
to tell you that what is the backbone of radio astronomy, that how the radio frequency telescope works. That was my primary intention to talk with. Okay, so
Okay, sir.
regarding this one, I think that maybe a radio astronomer can give a better explanation. So I'm sorry that I am not the
No, okay, sir. Okay, sir.
person to
Thank
give
you,
the
sir.
right answer. Yeah.
No, okay,
Yeah.
sir. Okay, sir.
Yeah.
Thank you, sir.
Yeah. And tell me the other ones that you are having some other questions also.
Yes, sir. Another question is, sir, suppose what you said, the receiver, the optical receiver at the end about multiplexing. Sir, how do you demultiplex? How do you demultiplex two waves at very close frequencies that come from a very distant source?
Okay. So what you have to do that when yeah. Can you listen to me? Hello, can you listen to me?
Yes, sir.
Yes, sir.
Okay, yeah. So what you are having that suppose you are having two signals operating at lambda1 and lambda2. So in the receiver end, you need also two signals lambda1 and lambda2. And this lambda1 and lambda2, so what you need that two distinct photodiodes, they are operating at exactly at these two frequencies of lambda1 and lambda2. Okay, so you have to
Yes, sir.
make those ones in a very distinct way. You have to make sure that it is operating exactly at lambda1 and the other one is operating exactly at lambda2. And once you are having the photodiode, so you know that you can easily then go with the demodulation. The rest of the principle of the photodiode you can take care.
Yes, sir. Yes, sir.
Yeah.
Okay, sir. Thank you, sir.
Thank you. Yeah.
Thank you, sir.
Other? Other questions, please.
Is there any question?
Hello.
Yes, sir.
Any question?
Any other question?
I think there is no question.
So that means either everyone has understood or everyone has not understood at all.
So
No, sir, this
we
is
have
very nice.
understood, sir.
Yeah.
Thank you, sir.
Yeah.
So, shall I conclude, Professor Bhattacharya?
Thank you, sir. Enjoyed the presentation very much.
Okay. Thank you very much. Thank you very much for
This is
all the
Aprotim, sir.
hospitality and sorry.
Sir, this is Aprotim. Enjoyed the presentation
Hello.
very much.
Okay. Thank you. Thank you. Yeah. Okay. Okay, Chitta, can I leave now?
Thank you, Professor.
Your voice is getting, that segregated.
Thank you for wonderful lecture, Professor Bhattacharya.
Thank you very much for inviting me. So,
Yes, we can conclude.
yeah,
Thank you.
So, yeah. Thank you very much. Thank
Yes,
you.
the signal is poor here.
Yeah. Okay. Okay. I am leaving. So currently, thank you very much to all of you for coming over here and listening to me. Okay. Thank you. Thank you.
Okay. Thank you. Thank you. Okay. Welcome. Okay. Bye.
Bye.
Okay. Go.